we're going to finish up chapter 4. We talked about changes in energy, and when you're talking about a chemical reaction, the most common change in energy is heat. And you can actually measure that, okay? There's a unit, a metric system unit, a system international, whatever you want to call it. But the unit of energy is called a joule. And the most common substance they use for determining that is water, okay? And what they say is it's the energy required to change 1 gram of water, raise the temperature by 1 degree Celsius. And for water, it's what they call specific heat is 4.184 joules. That's how much energy it takes. But you're like, yeah, so if you look at metals, they're all less than 1. Well, think about it. Metals don't hold on to heat, okay? Water does. And it's really, really important that it does that, okay? If water didn't hold on to heat, like during the day it absorbs heat, at night it releases the heat. If it doesn't release that heat, when the sun goes down, we die. All right? So it's really important, and water holds heat better than any other substance. So we're lucky that, the earth is a lot of water. Because again, once the sun went down, if we didn't have water releasing that heat, we would die. So, it's important that water has a high specific heat. Okay? That has also been converted to calories. When you look at your food labels, it says calories, but it's actually kilocalories. If you really want to change that to calories, multiply by 1,000. And if you took, if you're eating something and it has 200 calories, and all of a sudden it has 200,000 calories, that might freak you out a little bit. But, that's how they converted it into units that I guess make more sense to us. Okay? But again, heat and temperature are different. Okay? If you have 2 beakers and they each have water, and the temperature is raised 30 degrees, okay? The beaker that has twice as much water, it's going to take twice as much heat, okay? It's just not, heat them both up. If you want to raise the temperature of both of them and one has twice as much water, it's going to take twice as much heat. Now, when you measure heat energy, that's temperature. So temperature, some people think is just heat. It's not. It's a measure of the heat. It's a measure of the energy of those particles, okay? So while they're based on each other, they're not the same thing. Okay? So here's an example, methane. That's natural gas. That's how a lot of people get their heat. We don't around here, we get propane, which is the same process, except for CH4, we have C3H8, that's propane. But the process would be the same. Now, if you take a unit of methane and you add oxygen to it, because of course you have to have oxygen. And I don't know if any of you guys had issues with carbon monoxide poisoning, but when you don't have enough of this, then when you burn it, you get CO here instead of CO2. Now I'm rambling, sorry. Anyway, so when you burn any fuel and add oxygen to it, you get carbon dioxide, released in the air, water, and energy. And this is what we use, like I said, when we're heating our house or whatever. Okay? So this is an example of a reaction, and this is what we're looking for. We're looking for energy, kilojoules. Okay? And you can convert kilojoules to calories and joules to kilojoules. 1 joule, if you wanted to convert it, 1 kilojoule has 1,000 joules. So it's just like we did before with the dimension analysis. And the same thing if we want to change to calories. This is how many joules are in 1 calorie. And again, it's based on water because it's such a common substance. I guess it's popular too, but Okay, so if I want to solve for calories, if I wanted to change this into calories, I start with what I know. I got to change kilojoules into joules. So again, kilojoules on the bottom, joules on top. And then I also know that 1 calorie is 4.184 kilojoules. So I'm just going to take this times 1,000 and divide by 4.184. And that will give me my answer. And I'm sorry you can't see it. I'm in the middle. It's 1.9 times 10 to the 5th. That's how many calories that you would get when you burn 1 unit of methane. Okay? So it's easy to move things around. Okay? So every substance has a heat capacity, and they call it specific heat. It's the amount of heat gained or lost when you change the temperature 1 degrees. So 1 gram of a substance, 1 degree. Whenever you do that, how much heat, does it lose heat or does it gain heat? Okay? And that's specific heat. And again, for water, specific heat is 4.184 joules. Okay? Here's some other ones. And again, like I said, water is the best. Okay, here's its specific heat if you go that, but this is the actual number. Okay, here ethyl alcohol is half. You've got ice, and it's still important that ice has a specific heat because in the wintertime, we still need the ice to release heat at night, otherwise we'll freeze. I know it seems like we freeze in the winter anyway, but it really is releasing some heat to make sure we don't die. But then, like I was saying with metals, look at all of them are below 1. We said metals are conductors. They let heat go right through them. So they're not going to absorb it. It doesn't affect them like it does these guys up above. Okay, so when an object is cool or heated, either or, there's a couple things that are going to happen. Okay, you're going to transfer heat. Now, how much heat gets transferred depends on how much material you have. Okay, there's going to be a difference between 50 milliliters of water and a big gallon of water. Okay, the magnitude of the temperature change. Are you changing the temperature 2 degrees? Are you changing the temperature 200 degrees? So that makes a difference. And then what substance are you doing this to? If you're using a metal, it's going to be different than if you're using water. So these three things are what counts. So they're in the formula. When you're trying to find specific heat, there's a simple formula. Okay? M is the mass. How much material? C is the specific heat. Okay, and I showed you that on the slide before. They have a number. And this, anytime you see a triangle in science, you guys, it means change in temperature. How much did the temperature change? So you can use this formula to figure out. And Q stands for the amount of energy lost or gained. Okay, I don't know why it's Q, you guys. I wish I could tell you, but I don't. But if you want to figure out the heat lost or gained by a substance, you need to know how much it weighs, the mass. You need to know its specific heat, and you need to know what the change in temperature is. Okay, that's the formula for finding the heat lost or gained by a substance. All right, again, here's the numbers here, and if I go too fast, you guys just pause and then you can write it down. All right, so how much heat is needed to raise the temperature of 200 grams of water by 100 degrees Celsius? Okay, so we got the mass, we got by 10 degrees, so this is how much it's going to go up, and we know what water specific heat is. So we're going to take our mass is 200, our specific heat is 4.184, and it's joules per gram Celsius. I know it's a big long unit, but that's all in when you're calculating it, and the temperature. Okay, so you just multiply the three of them together, and you're going to get, again, it's in me, sorry, 8.37 times 10 to the third, or 8,370 joules. That's how much is released that's how much energy you need to raise the temperature 10 degrees. Okay, so it's actually pretty simple. You've got the numbers there. Okay, what if I want to find the specific heat? What if I have an unknown substance? And there is a list of all these, so you can actually identify an unknown substance if you can find a specific heat, because you do your calculation and then you look on the chart and you find the metal. Okay, so here we have heat lost or gained. We know the mass and we know the change in temperature. But now we're trying to find a specific heat. So if we manipulate the formula, okay, if we know this and we know this and we know this and we're trying to find this, all we have to do is start with our heat lost or gained, divide by the mass, and divide by the change in temperature. Okay, so we've got the heat that we gain. We know the mass of our unknown substance, and we subtracted these two numbers to get our change in temperature. So that's how you solve for it. You take 1638 on top, that's the total, the mass, 125, and then our change in temperature. And what that'll give you now is your specific heat. And that's where, remember I told you that weird joules / grams per Celsius, joules, grams, and then there's your Celsius. That's how it ends up being that way. And if you remember this, you'll remember how to set them up. Okay, so there's our numbers. And we get 0.475 joules, grams per Celsius. Okay, so 0.475, I know that's some sort of metal. Okay, I know it's definitely not water. Remember we said water was 4.184, and the metals are under 4. So if you look on the chart, you can find the metal. Okay, okay, so anytime you have a chemical reaction, again, remember they absorb or release energy. Anytime there's a chemical change, there's going to be a change in energy. All right, they can produce different kinds of energy. There's electrical energy that we use in batteries. There's heat, there's light, there's all kinds of, but there's going to be some sort of change in energy. Okay, Here's an example of a chemical change that uses energy. Here with our rocket fuel, you burn that and look at the energy that's given off there. We have, when we talk about electricity decomposing water into hydrogen and hydrogen and oxygen, sorry. Here's a big one right here, photosynthesis. You use the sun's energy and plants absorb it and make food and oxygen. Without that, we're toast, you guys, okay? The ultimate source of all chemical reactions, of all energy, is the sun. Okay? So, I talked about this before. I said that energy cannot be created or destroyed. Really, all we do is change it from one form to another. So, that's the law of conservation of energy. And I know that sounds a little strange because if you burn a piece of wood, now you don't have energy from it anymore. Well, you got energy from it. You got heat, you got light, but they were given off into the atmosphere. Now they're in the atmosphere. You can't get them back. So you change it into different forms, and sometimes you can't get that form back. Okay? Here it shows water decomposing, and it takes energy to do that. At one time, they were trying to get hydrogen gas because it would be a really clean form of fuel to use instead of the fossil fuels, but it actually takes more energy to liberate the hydrogen gas than it does the energy you get from burning it, so that needs work. Okay? All right? And again, they talk about this. Hydrogen, if we use it as a fuel, the problem is it takes more energy to get it than we get out of it. It's very clean burning, and that's actually what if you have a hybrid car, in your fuel cells, that's what they do. They convert water into hydrogen, and then you burn that hydrogen, and that's why it's no pollution or anything. And so they're working on it, and fuel cells are pretty cool, but you can't use them all the time. Okay, we also get our energy from wind, especially in North Dakota, because we can't get all our energy from fossil fuels. It seems like we can in North Dakota because we have a lot of oil, but eventually those will run out. Okay, so we get, I think in North Dakota we get 85% of our energy from fossil fuels, and there's this, I think there's a federal initiative that you have to get from other non-renewable or from renewable, which we're really lucky at the college. If you haven't noticed, the college uses geothermal energy and it uses wind energy, so the college is ahead of their time. Okay, and again, here shows you some of the things, some of the fuels that we use. When you get crude oil, you get all these things mixed together, and so that's what the distilleries do, is they separate them into components, and it's just a different ratio of carbon to hydrogen. Okay, so natural gas. I grew up in the cities in Minneapolis, and we used natural gas. It was piped into our house because they had a system to collect it and whatever. In North Dakota, we don't have that. So there's very few places that get natural gas, CH4. Most of places get propane where it's delivered. In Minot, I think they have Montana Utilities or something. They can get natural gas if they want. Okay, but it's in bigger cities. You won't see it out in the country. We all have tanks and they fill it up with propane, and that's what we burn. Okay, so it's a different system. But again, it's all plants that were squished, and depending on at what temperature they're squished depends on what they were produced. Okay, so we've had energy crises before, so we were like, you know what, we're going to run out of that stuff, plus it causes pollution, it causes global warming, so let's look at our other options. Okay, in North Dakota, this is top notch right here. Okay, and you've seen a lot of wind farms in North Dakota. This one isn't so great because we don't get a lot of sun in the winter times and stuff at the angles we're at. Biomass is another one. And again, in North Dakota, another huge one we use is geothermal. It's going down in the ground and taking the heat from there. Okay? And that's that. So we're done with chapter 4 now. Please do your assignment afterwards, and then we'll move on to chapter 5 next time we talk.